Ladies and gentlemen, today we're going to solve this ridiculously awesome double integral. And you may ask yourselves, why? Why on earth would we solve such a monstrous looking integral? Well, that's the entire point of this channel. All I do is solve beefy integrals or those nasty differential equations. Then there's the occasional physics video here and there, and a bit of formal educational content, more formal content on topics like complex analysis. But there is another point in solving this integral today. The Book of St. Gigachad clearly states in chapter Never Skip Leg Day, bro, there art not feats of peak masculinity greater than solving gnarly integrals and not skipping leg day. Yesterday was leg day for me. And today I complete the second half of that teaching by solving this integral. Anyway, now that we have an objective for actually solving this thing, we might as well get started. So we have the double integral from 0 to 1 of x times log x times the square of log y divided by 1 minus x times y dx dy. So the first thing we could do here is make use of the fact that the first integration is being carried out with respect to x. So we can take the squared log of y outside the first integration operator. So we have the integral from 0 to 1 of log square y times the integral from 0 to 1 of x times log x divided by 1 minus x times y dx dy. And now for this integral here, we could make use of a geometric series expansion. So recall that the reciprocal of 1 minus t can be expanded as the sum over the non-negative integers k of t to the k provided that the absolute value of t is less than 1. And this criteria is satisfied for x times y on our region of integration. So this implies that the reciprocal of 1 minus x times y in this case can be expanded as the sum over k of x times y to the k. And this further implies that the target integral I equals the integral from 0 to 1 of log square y times the integral from 0 to 1 of x times log x times the sum over k of x to the k times y to the k dx dy. Now this x times log x term is independent of the index variable k, so we can just slip it inside the summation operator here. So that means, let me just fix that arrow a little bit. I'm just making it worse. Much better. So this means that I equals the integral from 0 to 1 of log square y times the integral from 0 to 1 of the sum over k. Now x times x to the k gives us x to the k plus 1. We have y to the k as well. And we have this log x term, integration with respect to x, and then with respect to y. Now let's focus our attention on this part of the problem. So we'll switch up the order of the integration and summation operators and write this as the integral from 0 to 1 of log square y times the sum over k of the integrals from 0 to 1 of x to the k plus 1 times y to the k times log x dx dy. And because this y to the k term is independent of the x variable with respect to which we're integrating first, we can take it outside the integration with respect to x operator, and we get the integral from 0 to 1 of log square y times the sum over k of y to the k times the integral from 0 to 1 of x to the k plus 1 times log x dx, and we have this outer integration with respect to y. And now this integral here is pretty easy to solve. All we need is some integration by parts. So we'll get x to the k plus 2 divided by k plus 2 log x, with the limits being 0 and 1, minus 1 by k plus 2 times the integral from 0 to 1 of x to the k plus 2 times the derivative of log x, which is of course 1 by x, and that means we're left with x to the k plus 1 dx. Now the first term here collapses to 0, meaning that we have negative 1 by k plus 2 times x to the k plus 2 divided by k plus 2 with the limits being 0 and 1, which sorts out to negative 1 by k plus 2 squared. Okay, cool. So this implies that the target integral I equals what exactly? Okay, so we're going to have a negative sign outside. Integral 0 to 1 log square, terribly sorry about that, log square y times the sum over the non-negative integers k of, again, what exactly? Yes, indeed, we have y to the k divided by k plus 2 squared, integration with respect to y. Now, this log square y term is independent of the k index as well, so we can just slip it inside the summation operator, and we have the negative of the integral from 0 to 1 of the sum over k of y to the k divided by k plus 2 squared times log square y dy. Now if we switch up the integration and summation operators again, we have the sum over k of the integral from 0 to 1, negative sign, y to the k times log square y dy divided by k plus 2 squared. Now this k plus 2 squared term is independent of the y variable, meaning that we can write it as the negative of the sum over k of 1 by k plus 2 squared times the integral from 0 to 1 of y to the k times log square y dy. Once again, we have a very simple integral to evaluate here. Using integration by parts, we have y to the k plus 1 divided by k plus 1 times log y, limits being 0 and 1, minus 1 by k plus 1 times the integral from 0 to 1, y to the k plus 1, and differentiating the square of the logarithm of y, we get 2 times log y divided by y, correct? The first term again collapsing to 0, meaning we're left with negative 2 by k plus 1 times the integral from 0 to 1 of y to the k times log y dy, which is exactly the same structure as we had before with the x integral. And we had k plus 1 as the exponent of x, and that resulted in a k plus 2 squared in the denominator. So we're going to get negative 2 by k plus 1 times 1 by k plus 1 squared, meaning that we're left with negative 2 by k plus 1 cubed. But no, wait, I think we're definitely going to get, yeah, an extra negative sign. So that means they just cancel out, and we're left with positive 2 by k plus 1 cubed. Okay, cool. And all of this implies that the target integral I equaled, we had a negative sign, we had the sum over the non-negative integers k, and we had a 1 by k plus 2 squared thingy, and we have now this 2 by k plus 1 cubed thingy. Okay, cool. And if I transform the index from k to k plus 1, meaning that I can be written as negative 2 times the sum over the positive integers k of 1 by k cubed times k plus 1 squared. Now all that's left to do is evaluate this infinite series. And for that, the first thing I need is a partial fraction decomposition. So now that we have lots of terms instead of a single term, it's time to make use of the linearity of the integration operator and write this as negative of the sum over k of 2 by k cubed plus 4 times, wait, this is negative 2 times this infinite sum, and we have 4 times the sum over k of 1 by k squared, which looks quite familiar, plus twice the sum over k of 1 by k plus 1 squared, which could be reframed as the sum over k starting at 2 of 1 by k squared. And then we have one more infinite series. That's the sum over k of, wait a second. So we have, yeah, definitely a minus sign here. And that's 6 by k minus 6 by k plus 1, which is in fact a telescoping series, which evaluates out to, let me just factor out the 6 here, and this infinite series sorts out to 1. So that means the last term is going to be a negative 6, and you also have negative 2 times Apéry's constant, that's zeta 3, and then we have 4 times the Basel problem here, so that's going to be 2 times pi squared by 3 now, and we have twice this infinite series that is the Basel problem, but missing the k equal to 1 term, so we have pi squared by 6 minus 1, and this negative 6 over here as well. So that means we have negative 2 zeta 3 plus 2 pi squared by 3 plus pi squared by 3 minus 2 minus 6. So the 2/3 plus 1/3 gives us a whole 1, meaning that we have pi squared minus 2 times zeta 3 minus the number 8, which is a constant that I normally do not see in the problems I solve here on the channel. Numbers have become extremely rare, at least for the type of math that we do. We only do cool numbers now, things like pi, e, little gamma, the lemniscate constant, 69, 420, 0, 1, yeah, that kind of stuff. Anyway, so the number 8 is a welcome change here. And I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.